So, how can we now build MEMS systems that use magnetics for actuation? We have a number of different options to do that. Either we work with permanent magnets or magnetic materials. So, for example, permanent magnets. These are hard magnetic materials to generate a force, or we're going to generate a force by a coil mechanism or Lorentz force mechanism by sending a current through a wire and then using a magnetic field that is generated around the wire. So these are the two ways of generating a magnetic field. Of course, magnetic force is always an interaction between two magnetic components. So we're going to have on one way we're going to have two generating components that interact with each other. And either these components can be on the microsystem. That's what's this box here is the microsystem. So, for example, you can have a coil system interacting with another coil, or a coil interacting with a permanent magnet, or a coil interacting with a Lorentz force system. Or we can interact with an external field, an external magnetic field that we then provide in some way. The fourth magnetic interaction that we can, or way we can use to do magnetic interaction, is using lower reluctance materials, which are materials. They are soft magnetic materials. They're also specific materials. They are materials that conduct magnetic field lines, but are not magnetic themselves per se. So many metals, for example, will be good in guiding magnetic material. Like, for example, the door of your fridge is not a magnet, but it conducts very well magnetic fields. So therefore, if you put a magnet on it, the magnet will stick to the fridge. So we're going to now see a number of examples of how you can use these four different components and integrate them. The first example is that of the Lorentz force here. What is the Lorentz force? Well, the Lorentz force is the force generated between two conductors. So I have two conducting lines, and I have a current. Here you can see the two lines. And I have a current in one going in from the left to the right, and in the other from the right to the left. I will generate, of course, a magnetic field, in this case, that turns around in this way, and this one I get a magnetic field that turns away in that way. And these two magnetic fields will interact with each other, and that will result in a force between these two lines. And as a matter of fact, I think it's the definition of, I believe, the ampere. The definition, I think, of the Newton is if you send 1 milliampere, I believe, you have to look it up in Wikipedia, but I think if you send 1 milliampere between two wires of 1 meter length with a distance of 1 meter in between, you get a force of exactly 1 Newton between these wires. Yeah. So you can use that. You just make two conductors, send a current in opposite direction, and then you can use that actually to generate a force between them and use that force in an actuation. An example of such a system that uses that force is the following system. It's a Lorentz force-based gyroscope. This has been developed in Neuchâtel, the EPFL in Neuchâtel, by the group of Professor Nico de Rooij. Before I will explain how this works, it's a very beautiful system because it's very intricately made. Before I explain how this works, first I suggest you watch the next video, which is actually a short overview of what is the Coriolis effect that we're going to use here.